Hello everyone and welcome to the last video tutorial about MODULO. It's Davide here and today we are going to talk about the memory saving option. With this video we close this short course about MODULO. If you haven't done it yet, you should download the last release in the section release in our GitHub repository. This is the version 1.1.0 and has the new memory saving feature. In this video we will perform the POD with the memory saving for the exercise 5. In this exercise, the dataset comes from the time-resolved particle image velocimetry of the flow past a cylinder in transient conditions. This experimental campaign was done in collaboration between the Karman Institute and Dantec Dynamics and consists of 13,200 vector fields that were sampled over a field of view of 70 × 26 mm at a sampling frequency of 3000 Hz. You can find all the details of this interesting test case in this publication on arXiv. The main challenge here is that the dataset contains 13,200 snapshots with 4,740 entries each, and this can become challenging for many laptop computers, at least for mine. So, what are the computational requirements of a decomposition? Okay, let's see this in action. I am now working on a virtual machine that has 8 GB of RAM, and so let's see what happens if we try to do this exercise. We first need to select an exporting folder in testing modulo. We can call it trial, for example, and then we import our data. This is a 2D vector test case that presents a separated mesh format file. So we first need to select the mesh file, and then we import the entire dataset. Now let's wait for the opening of the region of interest panel. Here we go. Okay, now after clicking on Done, the importing begins. I will speed up this part of the video. Observe that we are now taking about 2 GB of RAM and we only have 6 left to proceed. We now select the POD and we introduce the sampling frequency that is 3000 Hz. And let's say that we want the first 5 modes. Now MODULO starts computing the temporal correlation matrix. And now it starts its diagonalization. And now the memory usage grows until almost 7 GB. Now the remaining part is not sufficient for computing the diagonalization and our computer will crash. So I will now pause the video and get my computer back to life. So let's see in details which are the requirements for a decomposition. As you remember from the first 3 video lectures on the theory of modal analysis, running a decomposition requires several matrix multiplications. If we consider for instance the case of the POD described in the second video lecture, MODULO will work with 5 matrices. In general, 3 of these, namely D, phi and phi sigma, are of sides ns times nt. Each entry of a matrix needs 8 bytes. So in terms of memory, these matrices require 8 times nt times ns times 10 to minus 9 GB of memory. You remember that ns is the number of spatial points in your snapshots, while nt is the number of snapshots. The other 2 matrices, namely k and psi, are of sides nt times nt, that in terms of memory is 8 times nt times 10 to minus 9 GB. So for example, if you have a database with 10,000 snapshots, each containing 30,000 mesh points, you will need more or less 8 GB to keep all of these in memories. If you do not have enough memory, you will not be able to do the decomposition. Here is where the memory saving feature comes to rescue. The idea of the memory saving is to avoid loading large matrices and begins from the partitioning of D. Let's say, for example, that we partition it in 4 and we save each of these partitions in a temporary file. We will then load in memory no more than 2 partitions at a time. This of course makes the matrix multiplications much harder. In the case of POD and MPOD, the first matrix multiplication encountered is the temporal correlation matrix, that is D transpose times D. To compute this with partitions, we proceed by blocks. So once each partition of D is read and saved on temporary files, we first load in memory the first partition and compute its correlation. We will then keep the first and load the second for computing the corresponding correlation entries. We can then proceed with the third and finally with the fourth. Recall that this matrix is symmetric, so we can save a lot of time by computing only one correlation and then mirror it. The loop can then continue by keeping in the memory the second block and computing the associated 2 correlations remaining, and so on for the third and the fourth partition. Notice that if nt is not an integer multiple of the partitions, MODULO will readapt the dimension of the last block automatically. Let's see this in action. We now import again our data and this time we activate the memory saving feature. This pop-up below is enabled and it allows to choose the number of partitions. MODULO will always propose 3 options that are based on the current available memory. Let's say that in this case we select 4. Now the importing does not start because T is not constructed. We now select the POD and introduce the same parameters as before, so 3000 as sampling frequency and the first 5 modes to be exported. So now I will speed up this part of the video while I will keep talking. If you look in the folder where we have our executable of MODULO, we will find a temporary folder called temp. In this folder, all the temporary files will be saved. The first you will find are the partitions of D. They are 4 because nt, in this case, is an integer multiple of 4, that is the number of partitions. Otherwise, we would have had another smaller block. Once the partitions are ready, MODULO proceeds with the computation of k. Observe that now there's much more memory available and we can complete the decomposition. Few moments later, it will continue with the diagonalization of k. After the diagonalization of k, it will start computing the modes, and the final projections are performed by blocks. So, let's pause the video and let's go back to the theory of the memory saving to see what happens in this case for the final projections. So, by working with blocks, we have solved the problem of loading the data matrix T, and we have computed the temporal structures. However, to compute the spatial structures, we need again our matrix T for the final projection. You recall from the second video lecture that this is done by multiplying D times psi. So, we must proceed with partitions again, but this time using row-wise partitions. So we first reload our previous column-wise partitions and save them as row-wise partitions, as shown in this slide. Then we can perform the multiplication by blocks, obtaining the corresponding portions of the matrix phi sigma. Each block of phi sigma is then saved on temporary files. The dimension of these blocks is no longer nt over partitions, but is now ns over partitions, that is this nr here. Also in this case, notice that if ns is not an integer multiple of the partitions, MODULO will automatically readapt the dimensions of the last block. The last step depends on the decomposition. For the POD, we already have the sigmas stored from the diagonalization of k, so we only need to restructure these row-wise blows into columns each containing the spatial structure. This final step is very fast for the POD because the modes are already sorted and we can focus on the modes we want to export. So let's see this in action. You can see that the portions of the matrix phi sigma are saved on temporary files in the same folder called temp. In this folder there is also psi-p, that is the temporal structure of the POD, obtained from the diagonalization of K. Then each spatial structure is saved on a different temporary files. So in this case we have 5 temporary files for the spatial structures because we want to export 5 modes. Modulo reads them back and exports them in the usual Excel and PNG format that you have seen in the previous videos. You should double check with the other exercises that the results obtained with the memory saving are the same as the ones without this feature. You will see that the memory saving generally takes more time because of the many writing and reading operations, but you will see that this is an acceptable price to pay if you do not have enough memory. So to conclude this short video, let's see how the memory saving handles the other decompositions, namely the DFT and the MPOD. In the DFT, we initially save a lot of time because we actually do not have to compute psi-f. The projection d times psi-f can be done using the popular FFT algorithm over the rows of d. On the other hand, the number of modes that will be computed will always be nt, even if we want to export only the first 5 modes. Moreover, after the projection, we do not have the sigmas, so we need to normalize each of the nt columns of the matrix phi sigma to compute them. This is why the DFT will always take a bit longer than the POD. In the MPOD, the computation of the psi-m is more expensive since it involves the diagonalization of multiple correlation matrices, unless we use the fast MPOD algorithm. This, as you have seen in the previous video, is still under development. The advantage over the DFT, however, is that we generally do not compute all the modes, especially if we want to export only a few of them. You can play with this using the cutoff parameter in the MPOD interface. If you only want to export 5 modes, there's no need to compute more. So in this last step, we save time over the DFT. I encourage you to test both the DFT and the MPOD with the memory saving and see what is the largest dataset that you can still decompose with your computer thanks to this feature. So, as you might have guessed, the bottleneck will always remain the diagonalization of the correlation matrix for the POD and the MPOD, while the DFT is not limited by this. This will certainly be in the next release of Modulo, but for the moment the scope of the memory saving feature is to ensure that all your memory is given to the diagonalization and you save a lot of memory during matrix multiplications. So, I thank you for your attention and I invite you to follow the Modulo project on ResearchGate for news, new releases and updates. Goodbye!